The physical world operates in a state of constant, chaotic motion. It's continuous and messy, and filled with massive kinetic forces, like the thousands of pounds of pressure slamming down in a metal stamping press. When we attempt to harness those massive forces at scale, like containing the explosive thrust of a rocket engine during liftoff, we must monitor exactly what's happening, second by second, to keep things from going catastrophically wrong. But that creates an immediate problem. Our modern control systems are built on microprocessors, and computers only understand discrete binary code, ones and zeros. They are naturally blind to continuous physical properties, like rising heat or mounting pressure. To automate any physical process, we have to find a way to translate the continuous reality of the physical world into the discrete mathematical language of software. That translation bridge is called a data acquisition system, or DAC. It's the dedicated hardware and software pipeline built specifically to convert physical events into computer-readable data. The macro architecture of a DAC follows a strict linear sequence. It starts out in the field with a physical event, which is detected by a sensor node. That physical reading then passes safely through a signal converter and finally feeds into a software interface on a monitor. Because the conversion happens at incredibly high speeds, these networks maintain continuous monitoring with near-zero downtime. The entire pipeline functions as a digital nervous system. It gathers millions of data points, allowing human operators to safely manage massive, complex industrial plants entirely from remote screens. Let's look at the first stage of that pipeline. The actual senses of a DAC system are devices called transducers. Their specific job is to take a physical change in the environment and turn it into a proportional electrical signal. For example, a strain gauge measures applied force or weight. As a heavy load bends the gauge, that physical deformation directly alters the internal electrical resistance of the device itself. Or consider an LVDT sensor. Instead of measuring applied force, it tracks mechanical displacement, generating an electrical current as a moving core slides precisely through a series of internal coils. To fit these mechanical sensors into tight spaces and run them on incredibly low power, manufacturers print them using photolithography. By using UV light to etch complex sensing structures onto microscopic silicon substrates, they can shrink heavy industrial tools down to the millimeter. But whether the sensor is tracking heat, pressure, or a sliding mechanism, the output at this stage is always exactly the same: a raw, continuous, analog electrical voltage. That raw analog voltage is rarely ready for a computer. It is usually far too weak or packed with chaotic electrical noise from the surrounding industrial environment. To organize this efficiently, engineers use multiplexers. These hardware components gather dozens of distinct analog sensor signals and funnel them into a single processing pathway, cutting down on massive amounts of wiring and cost. That pathway leads to the analog-to-digital converter, or ADC. This critical translator takes a continuous wave of voltage and sequentially slices it into thousands of discrete binary numbers. By converting flowing currents into rigid data points, it formats physical reality perfectly for a microprocessor. Raw binary data requires a programming environment to be useful. Here, the Arduino IDE, or dedicated PC software, steps in to interpret the measurements. Software provides the logic. It continuously compares the incoming sensor data against pre-programmed safety thresholds. If a pipeline's pressure spikes past a safe limit, the software catches it in milliseconds and automatically triggers a mechanical response. To keep human engineers informed, the software builds what are known as mimic displays. These graphics give operators an intuitive, real-time visual map of exactly what is happening inside a remote facility. Operating these networks does require balancing physical limits. While the software layer processes data at lightning speeds, the physical sensors out in the field remain highly vulnerable to extreme temperature shifts and physical structural wear. Ultimately, it is the software programming layer that elevates the system. It takes a passive string of measurements and turns it into an active, decision-making control loop. Today, this architecture forms the backbone of Industry 4.0. By networking DAQ systems together with highly sensitive smart sensors, modern factories have moved past basic mechanization and into true predictive automation. On manufacturing lines, continuous sensor feedback does two critical jobs at once. It monitors the precise quality of the product moving down the conveyor, while simultaneously tracking the mechanical health of the machinery building it. The stakes are even higher in aerospace. Advanced aircraft rely entirely on instantaneous data processing to measure drag, monitor fuel, and maintain aerodynamic stability. Because these digital pipelines can be miniaturized and run on tiny amounts of power, they are now deployed globally to monitor vast environmental metrics, tracking exact changes in our air and water quality. By perfecting the translation of physical forces into programmable binary code, data acquisition systems allow us to measure the raw environment and instantly turn it into actionable intelligence.